Hello everyone, my name is Richard Kaandorp. I'm the coordinator of one of the first modules, Applied Control. Applied Control is, together with Systems Modeling, the starting module of this master program, Engineering Systems. It's a common module for all master tracks. It contains 15 credits and it lasts one semester. It has various courses. We will discuss these courses also. And it uses this information in minor projects. So you're going to do a project together with 4 or 5 students. And students are full-time or part-time. So we mix all the groups to form a nice project group. The main purpose of this module Applied Control is controlling a process. Controlling a process which could be mechanical, electrical, or an energetic one. And you're going to design an analog or digital controller to go from a process to a controlled process. So the first step is generating a model, a mathematical description of your process, trying to describe the behavior of that process. The next step is that you design a controller. Because you have a model, a mathematical model, you can design a controller in software. And after you have found the right controller, you implement it with a certain platform into the process. That platform could be LabVIEW, MATLAB Simulink, or CodeAssist, for example. In this module, you have some content, some courses, feedback control, digital control, so the analog and digital control theory. Also some special techniques, applied control strategies, in which you encounter cascade control, for example. And you have optimal control. So if you are able to design a controller and you have to choose within a certain boundary the best controller, we call that optimal control. The next is controller implementation, in which you have to learn how to implement the controller into the process. Together we do a minor project. That's group work with 4 or 5 students. Let us discuss basically the outlines of the courses. So the first course is feedback control. Feedback control deals with classical control theory. You will first have a look at the process description itself. And that process description has been learned in introduction modeling, which you learn in systems modeling, and we build upon that knowledge. The next step is designing a PID controller with help of tuning methodologies. So we have a PID classical controller, a lag lead controller, or a digital controller, which you can design. We use some specifications, some design specifications or requirements. Otherwise, we don't have the best controller. And also, at the end of this course, some specific techniques will be taught. Like wind up and the solution to prevent that, and also dealing with serious delay times, and we call that using the Smith predictor. The next course is multivariable systems and optimizations, basically optimal control. What you see in this picture is a motorcycle driving along a way. The way is a gray path, and within that gray path you can choose various optimal solutions or various solutions. The red one, the yellow one, the blue one. But the question is, what is the optimal one? And we can use mathematics and we can use MATLAB Simulink in order to decide which path is the best path. And that's what we learn in this course, optimal control. After feedback control and some optimal control, we can have a look at special structures. Special control strategies. For example, cascade control, override control, or feed-forward control. And you can use special structures to deal with specific problems. In 80% of the problems, PID control will solve your problem, and that will be the solution. But in the remaining 20%, you need to do something extra. And that something extra could be a control strategy. In this example, you see a water cooler, a water oil cooler, in which you see two controllers, a pressure controller and a temperature controller. So this is an example of using two control strategies to control the apparatus of the water oil cooler. And we call this a cascade control structure. Another course, or actually some workshops, will be controller implementation. You will have to learn how to implement your control algorithm into or combine it with the process. So you have to put it into a certain program, a platform, and you can use LabVIEW, MathWorks or Codesys, a PLC program, in order to write a software program that will control your process. And in these workshops you learn how these platforms work, how you should program them, and finally you will use one of those platforms in your minor project. So controller implementation is building the bridge from the software package into the practical application. The last part in discussing all the courses is the minor project. It's not really a course, it's a structure to work together. And we start in the beginning of this semester, week number 3, with the kickoff of the projects. And you will form a project group in order to analyze a process, define a mathematical description from that process, design a controller, and as a last step, implement it into that setup. And you will do some measurements and you will show that you control the setup using control algorithms and software. At the end of the minor project, you will give a presentation, you write a report, so you show what you have learned in this course, in this minor project course. A few projects which come by in another video, but here you see some pictures of those projects. So motor generator, next to it in the middle you see a column, a water column, or the lock and key setup, in which you have 2 servo drives to control the key position, or the temperature of a room. That's in the lower 2 pictures, and on the right hand side you see a level, a tank level. So those are real setups to be controlled in the minor project situation. We also do other projects like a truck. You can platoon with the truck and you can have a look at the distance between 2 trucks, or you would like to control the position of a drone. And also underneath you see some infrastructure. Also smart infrastructure uses algorithms, uses some controllers to control the traffic flows. And the lower part you see an automotive project, a throttle valve used in combustion engine, and the position of that valve has a controller, a PID controller, which sets the valve to a certain position. Let's have a look at the schedules for the 2 terms, the first term and the second term. In the first term you will have the course feedback control. It lasts 8 weeks, and at the end of the 8 weeks you have a written exam. Then you see the digital control, but that will be in the second term. And the course multivariable systems and optimization will be in this first term. After 7 weeks you will have a written exam. So 2 written exams indicated as a red box at the end in week number 9. Furthermore, you will experience some knowledge from the platforms with controller implementation. So there will be some workshops on LabVIEW, PLC and MATLAB Simulink, and at the end also HandTune in this first semester. So we take 4 lessons for that in this schedule. And the last part will be the minor project. We kick off the project in week number 3, and after you gain some experience on the platforms, we will introduce the projects and you can choose a project which you like. Then there will be a few project sessions in this first term to work together with other students. After one term, you will have to create a project plan, a description of how you're going to tackle this project in the next term. The next term is term number 2. It's the second block, second term in this first semester. You have 3 lessons feedback control. The last 3 lessons will deal with the frequency domain. Then there will be a new course, digital control, 8 weeks of lessons. And finally, that will end into an assignment in a home taken exam. And we will combine 3 lessons of feedback control together with digital control into one written or one home taken exam. That exam will be given to you in week number 4, 5, so you can work in the last weeks of this second term on this home taken exam. The course Applied Control Strategies is nice after you have followed feedback control. So then you learn some special structures in controlling your setup. You can use that information also in your minor project. 8 weeks with 2 lessons a week, and it ends in a home taken exam. These home taken exams are two home taken exams in this course, and they will be given to you after week number 4 and week number 6. Controller implementation has 2 guest lectures in this second term. In the second term you will see some real projects. We invite guest lectures from our research institute to present you some actual applications of control theory. Controller implementation ends this term with a home taken exam in which you look back on the whole semester and how you implemented the controller into a platform trying to get the setup running. The last part, Applied Control Project. You will see this is the second part of the project work. You still work together in the same 4 or 5 students, the same groups. You have a few sessions and we start with a peer review to see how things are going. And at the end of this project, you will create a report, a project report. You will do that according to a template. So a structured way to report your findings and give a presentation finally in week number 10. Short overview of the exams. After first term you have 2 written exams, and in the second term you don't have any written exams, only a few home taken exams, and you finish your project with a report and presentation. Don't think that is easy, of course, because this takes a lot of work, but you have to do it yourself and not really an individual written exam. We use Onderwijs Online as our learning environment. We put on the PowerPoints, we have additional information, articles, scientific papers. You will find all that information on this site, Applied Control within Onderwijs Online. Hopefully I gave you an overview of this module Applied Control. We're going to do this the first semester next year, and if you have any questions, feel free to send me a mail. Thank you.